All right, good afternoon. Welcome back to our series on the NFL Big Data Bowl for the 2025 Kaggle competition. We are continuing down our trend of trying to improve the models to predict the routes run on a given play. If you remember last time, we had pulled the data together and created three types of models. One was the logistic regression, then the support vector classifier, and the random forests model. So I'll quickly go through and review what we've done before, and then we'll get into today's work on making some of those improvements. So if you're here for the first time, we started by going through a data discovery phase to better understand the data that we were given as part of this competition. Turns out we have information about each of the games. So who are the teams that are playing? What was the score of the game? Then there are the players. This is information about what position do they play, what is their name, what school did they go to, how long have they been in the league. And then there's this play information, which contains the information on a given play. Let's say that it's across all the games that happen. So it will be like one specific play out of the game. It will say, pass complete to Justin Jefferson for 8 yards. It won't include a whole bunch of specific information. That's what this player play data is for. So this is a combination of the players in play. And so it's for a specific play and that player involved on it. What were they doing on the play? Things like, did they catch the ball? Were they a receiver in the play? Did they move before the ball was snapped? Those are all relevant things that we've looked at so far that are contained within the data set. And then things like how many yards did they gain? Did it result in a touchdown? Things like that. So what we saw here is that this data is actually pretty full in the overall data set. So it's already been cleaned up significantly, which is a great place for us to start. But you'll see some of these that are very specific edge cases that if we hadn't looked into the data a little more, we wouldn't be aware of. So, for example, this yard line side, there's 224 rows where the data is missing. And it turns out that these are the plays that are happening that are at the middle of the football field, where it's not one team's side versus the other. It's actually like a neutral part of the field. And then there are plays here where there's no offensive formation or receiver alignment information. These are the kicking plays. And so what ends up happening on these is that there's no formation set because it's the kick. And that's why that information, the offensive formation is there, and also the receiver alignment as well. Then you have ones that are pretty straightforward, like the pass result and pass length. Well, if it's a running play, it's not a pass, so there wouldn't be information here as well. Then we took a look at trying to just get some high-level information on these given plays. And so we just were trying to take the mean of the rushing yards, and that gave us a result of less than a tenth of a yard per play, and that seemed significantly wrong. And that's because that data set is all the players on a given play. So 21 players will have no rushing yards on a rush play, and one player will. And then on the pass plays, no players will have any rush yards. So that significantly brings down this number. But then we found that there is a flag field here of who had the rushing attempt and then getting their rushing yards from the play. That brings us to a more reasonable average of about 4.5 yards. Same thing happens on the completions. The average completion length is about 10.9 yards. And then now that we are more confident in our means, we can then start to do some groupings in the data. So this was like grouping by the team, going through and then sorting it in order. So now we have the team with the best rush versus, if you go here, we did the inverse order, and that would give us the team with the worst rushing offenses. And then we started to group the data together so that way we could begin to build up the data set that we were going to use for the model. One of the things to call out here quickly is that you will see these numbers with really high averages are because they had very few attempts. So this might have been a trick play that worked once or twice. And so, or it might have only worked once. They tried it again, did not work very well. So they had a really good outcome the first time, but the second time, not really doing that much. But as far as our data set is concerned, like these would be outliers in terms of trying to figure out the averages for the best. And so you would do additional filtering on those. And so you can see here by saying that they had to run the ball at least 10 times to be in the list of average or best average rushers. We can see here Taysom Hill is one of the best. He's got 38 rushes. You can see right up against the edge of that is JaMychal Hasty here. So we set the cutoff at it needs to be more than 10. Well, exactly at 11, JaMychal Hasty still has one of the highest averages here. Then we put a flag field into the data set for was there motion on a given play. So as long as any one player moved, the whole set gets flagged for that play. So simply, if there's one person that moves, we're going to set them all for that same play ID. And then we started to look at information around passing. And so we saw there's a difference between the pass receptions and pass completions. So we wanted to make sure that we pulled those together, of making sure we had the plays that there was a play where the quarterback had dropped, and then add the passing yards to that, so we have an idea of not just the pass completions, but now the full passing spectrum of completion, incompletion, interceptions, things like that. This large cell here is how we group together our data on a whole. We take the rushing information, again, those dropback attempts, the passing yards, we merge them together. And then we add the names of the players on a given play to that data set. And then we start to pull in more information around it. So you can see here what was the result of the play, who are the receivers, quarter down, distance, things like that. So we have a more complete data set. And then we also worked to incorporate who were the players on a given play. So we're only pulling in the offensive players on a play to get an idea if that would improve our model. And as you'll see later, it helped some models and it made others worse. So it's good information to have, but we'll work today as well about doing some more isolating on here as things like including the linemen, who are typically pretty stable, like it's heavily related to the team. So you would want to remove those from the data set. So then come down here and we're all ready to go to start building some visualizations to better understand how teams performed. You can see from this image here, the majority of the teams were in shotgun for most of their snaps. There were a few teams that were not. For example, here, Atlanta and Baltimore, they actually ran heavily out of the pistol formation with similar matches in terms of the shotgun and then the single back formation. You can see teams here like Dallas ran mostly out of single back, same thing for Detroit, and then those other ones are smaller. So the size of the bar here represents the percentage of plays, but you can see there is variance across teams and how they approach. But the most favored by far was the shotgun formation, and then followed closely by a single back. Then we put together a graphic in terms of the overall team's offensive performance. The idea here is we're comparing the average pass yards versus the average rush yards. Now, this only takes into account the completions when we made this graphic. So ideally, you want to be up in this upper right-hand quadrant. What this means is that you had above average passing and above average rushing, and the more up and to the right you are, the better your performance. So you would say like across here, you probably have like the four most efficient offenses. But again, this is not factoring in incompletion. So you can see these kind of drop back more towards the line once we have an idea of what their outcomes look like in terms of completion percentage. But the idea here is that you want to be up and to the right. You don't want to be down and to the left. These are teams that had below average rushes as well as passing attempts. So you can see here that sometimes these feed into one another. For example, we looked at Tampa Bay individually, and what we saw is it was pretty easy to tell if they were going to run the ball versus pass the ball based on the formation that they were in. If they were in shotgun, it was something like 80% of their plays were likely to be a pass. And then if they were in the single back formation, then it was 80% the other way, 80% likely to be a rush versus doing a pass. And so defenses kind of started to figure out once you're in that formation, they have a better idea of what they're going to do and can adjust their coverages accordingly. When we're trying to build up the first wave of predictive models, we were trying to predict run versus pass. And so we needed a field here for that. So we made a flag called rush. If there were rushing yards on the play, then we called it rush. Everything else was going to be a passing play. Now, our first model that we had built was very basic and was based on 4 pieces of information: the rush field, which we were trying to predict, but then who was the team that was starting the play, what were the formation that they were in, and how were their receivers aligned. the idea here is that these are all things that you can tell pretty easily right before the snap on what they're going to be, and then likely the case. So this is a very bare bones model, just kind of proves out the concept of what we can do. And you can see here, just those 3 pieces of information being used in the prediction led to about a 70% accuracy rate. Now you can see here that there's a wide range being covered here. So predicting run versus pass, it was way better at predicting run than versus pass based on this base model. So it just needs more information. You want these to be closer to one another. And so you don't want a distance or a difference of about 6% between the 2 groups. Ideally, you want that somewhere around the 2 to 3 range. So then we worked to expand the information that we were feeding to the model. This is some of that game situation information. So the first one here is just getting the score differential of the team when they are on offense. So if you were the home team, then it's home minus visitor. If you're the away team, it's visitor minus home. I also did some experimentation with bucketing. So instead of using yards to go as a number, could we use it as a very simple 3 simple buckets? Short yards, you'll hear this described by the commentators on a game. You hear like 3rd and short. That means that there's 2 or less yards to get a first down. And then 3rd and long is typically anything like greater than 7 yards. And then the middle is just everything else that's between those. In terms of the absolute yard line number, these numbers are fairly arbitrary, but follow a little bit of the logic of football here. The absolute yard line number for these short absolute distances, this is basically the red zone. Once you've got 20 yards left to go for a touchdown, then we're going to call that the short field. The long, I said, was anything greater than 50 yards. This would be areas where teams would not attempt to kick a field goal. And depending on their kicker, there would be some adjustments to this. And then the mid-range would be anything between that red zone area and where you can no longer kick the ball. Also had to make adjustments to the game clock for the amount of time remaining in a game. So if we're in the first quarter and there's 10 minutes left, well, there's actually 55 minutes left to go in the game. And so that's what we did here is we would add in the first quarter 45 minutes to whatever was on the game clock, second quarter 30 minutes, third quarter 15 minutes. And then the game situation changes a little bit when there's 2 minutes remaining in each of the halves. You'll hear, or when you're watching the game, you'll see this referred to as the 2-minute warning. Teams start to play a little bit differently around this because it's their less chances to score, whether it's before the half or before the end of the game. Because at the end of the game, there's no more chances for you to score. At halftime, the current drive ends, and then it will restart at the third quarter. It'll be the opposite of who kicked the ball. Will then be whoever kicked the ball in the first half will be receiving in the second half. And so these situations are a little bit different, and teams treat them differently because there's very little time left to score. And so you're more likely to see a lot of pass plays during this time just to try and get more out of the clock time that you have available. And so this also tracks when we look at the buckets that are left when we do these. So there were 762 plays that were taken in the final 2 minutes of a given game here. Part of that is when you look at the overall number, right? There were about 13,000 total plays. These 2 buckets combined are about 10% of the plays that happen in a game. And then most of them happen at the halftime. And part of that reason is that when you're up by 2 scores, the final 2-minute warning, you're basically going to kneel the ball 3 times and then kick it away, or like to run out the clock, or you may have one more play to generate that first down, and then you're going to go into that same mode of action there. And so there's less plays that happen in those final 2-minute warnings, just because there's a lot of times where the game is no longer in hand, and so there's no reason to really run out those plays and try and score points again. So then we updated our model to include all those game situation information. So you see things, these were our original fields here, and then we added more information like the quarter, the down, that bucket for yardage to go, the distance, was there motion on a play, and then how long is left in the game. That's the 2-minute warnings there. When we worked to incorporate that, we actually got a model that was around 74%. And you can see here the precision and recall score is much closer. And then this is where we went and we said, well, maybe if we add the players to a play, we're more likely to get the results or get better information about the results. And running this through, we actually saw a small decrease by including this information in the logistic model. So another thing to do was to change the yards to go and the distances to treat them as numbers instead of using those buckets. And we see that we get a small increase by doing it this way, and then come back, okay, well, maybe we get more information on the players, and no, this goes down by like a full percentage point now. So what this is saying is that the players on the field do not matter as much to the predictive model compared to the information that it gets about the game situation more broadly. So what quarter is it? What down is it? How many yards to go for first down? What's the score differential? Those are more important than knowing necessarily who is on the field for a given play. And then we did the same thing with a random forest model. And we see here, random forest actually performs better with the player data. We get to about that 74.5% when we have the players, and then 73.5% when we don't. So that's one of those cases where actually adding more data is useful, and that's generally true for the random forest model. Now, the trade-off here, though, is that it's harder to explain what's happening in random forests when you are trying to work back from the model and determine what exactly is the information being used in terms of the prediction. Support vector machines is kind of a midway point between the logistic model and the random forest. It's a little harder to explain, but it is possible. And then you see here, with the player data, we got to about 73%, but without the player data, it was only 70% in terms of prediction. So the best model out of all these is actually that logistic regression. It takes the least amount of time. It also gives us the best overall results as well. So it's a good model, and it's very good at predicting a lot of these either or cases where you have something that is very binary in nature. Logistic regression is typically going to be your best performer there. But as you saw, we have to be careful with the information that we're giving it, as we added the player information in there, and it didn't particularly help the overall performance. And then last time we were working on going through and trying to predict the routes that were going to be on a play. We did need to add more information here. So we needed to figure out who the defensive team was. So we figured that out from the information, just knowing, is it the visitor? When team's the home, well, then you know that that's the defensive team. If the team is not home, well, then they must be the visitor and the defensive team. We looked at the receivers who was running a route on a given play. You will have multiple of players running a route on a given play. So this will make our data set larger. So we had about 13,000 rows before, when everything was fully incorporated. Once we have this, there are 28,000 plays where a receiver or 28,000 rows of receivers running routes. So from the information earlier, we saw that there were about 7,000 plays. And so on average, you have about 4 people who are running routes on a given play. Then we took this information and put it into a model. We didn't make this a logistic regression. We are looking at the route runs. There are about 12 different routes that a receiver can run on a given play. This NFL ID field is the given player on a play to know who they are in terms of their ID in the data set. You can always add their name afterwards. It's just easier to go off of the ID. And then we're including things like formation, what team they are, who is the defending team, what is the receiver alignment before it, and then a lot of that same quarter down, motion, and distance. So when we ran this model, we got about 30% accuracy, which if you consider the number of classes that this is trying to predict here, it's actually pretty good performance for the logistic regression. It was better than I thought it was going to be. I thought this would be somewhere in like the low teens to single digit area, but it was better than I had thought, given that we hadn't given it a whole bunch of information. And as you can see here, as far as the groups go, the overall size of the data set was about that 28,000. Taking about 20% of that means we have about 5,000 combinations to predict. And you can see here, a few of these routes only appear a few times. For the most part, they're in this, there's a group that's in this 200 to 500 range. And then there's a few routes here towards the middle that are heavily goes. So you'll see a lot of flat goes and hitch routes, and then less of those other ones. So you can see it basically had tried very hard to predict these. And that's why you see such variation here in the precision and recall scores. So it tended to over predict some of these groupings rather than really focusing on like the key amount of routes that were being run. Because you can see here, it had a pretty decent distribution precision-wise, but recall was all over the place. We also ran this through the same SVC and random forest map. SVC performed about the same. This is generally a better model in terms of classification than logistic regression. So it was interesting to see that we'd only gotten about the same performance otherwise. You can see here in this case, again, the recall scores are all over the place. It didn't predict any corner routes at all. So it's like it completely missed a couple of the classes. The same thing here for screens and then wheels. So some of the groups, it just didn't even try and say that it thinks that's more likely to be some of the others. So this would be something, if we were focusing on the SVC, we would like dig into more on why did it predict certain classes, one versus the other. And then the last group here is random forest. And I was surprised that it had performed so poorly overall, only 22% accuracy. And then breaking down the scores a little bit, it was kind of all over the place. It also tended to not predict these corner routes. It did predict them, but very, very few. It didn't even bother to predict the real route just because it was so rare in the data set. And then we did the same thing, but thinking, well, maybe player information here would be more useful on who the given players on a play are. And we see as far as that logistic model, it actually decreased our accuracy slightly. We went from that 29% down to 28%. For the SVC model, it's, again, a little bit of impact to it. We lost about, I think it was like 1.5% here. And then as far as the random forests go, it actually made it worse here as well. This is still running this one. It takes far longer for these when we add in the player data. But you can see here now your accuracy is in that 20% range, which is not great. So there was one other model type that I wanted to try, and that was the decision tree classifier. So what that does is it determines points along the way in the data to basically break it into different pieces. And I wanted to see if we could get better output here by using a decision tree rather than the other models, because this should be our best classifier model in general, but it may just be that we are not providing good enough data. Another idea is after we do this is trying to figure out who the eligible receivers are on a given play and see if that affects. So instead of giving it all 11 players on a play, could we perhaps give it to 4 or 5 people who are the tight ends, wide receivers, and running backs on a play to see if that will impact the model performance, right? Remove things like the lineman and the quarterback, because that may not be particularly helpful. So we'll work through the decision tree classifier now, and then we'll go through on how to actually break that down. So I'm going to take this here. It's very similar to the same things that we've done for random forests. There are some small differences here. So instead of this ensemble, we're going to call the tree method. And then this random forest classifier should now be a decision tree classifier right there. We also then need to take that information, change it to the classifier model. We're going to keep the same random state. The decision tree is a little bit different. We want to see how far down or how many decisions basically it can make to do a prediction. So typically what you would see in a very wide data set with having the player information is you would want at least a decent amount of doing this. I would say we would probably say 2, 4, 6, 8 levels down at most. There's going to be cutoffs for this, but I don't want to include the player information for the first iteration of this. And so let's do, I believe it should be depth. Let me just double check here. It's max depth. Let's say 6 here. I'm going to keep the same set. We've already split the data into this DT model. We've already split the data into training and tests, so I don't need to do that again. Once it builds that, we're going to then make it. We're going to then predict, but this needs to go off of T. And then DT model accuracy is now getting the accuracy score of that test. And so change that to DT as well. And then the classification report of the the test versus the prediction. So it looks like it had finished running that. Let's see. Do I need to change anything here? This is the train test split. Numerics. Processing. I think that should be fine. So we'll kick off that learning. Well, that was extremely fast. So at the depth, let's see, it predicts mostly that they're going to try and do flat routes and go routes. Doesn't look like it really predicted anything else. They're just too small. And so only 22% accuracy there. I wonder if we can show confusion matrix. Yeah, so let's do that. Oh, wait, I'm on the wrong row. Sorry. No wonder why that came back so quickly. Well, okay, so this is this should be DT. This should be 6. DT model, DT, DT. Okay, we're going to copy these down and then we're going to go back and fix those. You see that there, and then this needs to go back to random forests. So this should be estimators. Okay. So we see that this was actually slightly worse than the random forests in terms of the overall output, much faster. Overall, looking at the prediction matrix here, we get a better distribution. I'm surprised there's such a wide range here in precision recall in some classes and then not the others, especially this go route. Seems like it heavily blindly predicted this, and then it was just completely off. So let's, like I said, we'll make a confusion matrix. So we can go from sklearn, metrics, import, and then there we go. And the idea here, of that, it basically put most of it together. Let's give it a title. We'll call this the confusion matrix. Predictive confusion matrix, right? And then we'll want to show that. Yeah, and so what you see here is that it heavily predicted go routes in terms of what it was trying to say. So what does this look like? Like 80% of the data it predicted as a go route versus what it actually was. And so that's why there's such huge variance. So it's not having enough information here. I know this includes the player data as well. So maybe let's go back a step. And come to here. Because this ran fairly quickly, I'm not too concerned about the time it will take. So I want this to be our information. Not much improvement of knowing who the players are versus not. Look here, and once again, it's basically saying that most of the time they're going to run a go route in terms of its prediction, and that's not very useful information to know. I wonder if we do, but if I do from the estimator, and for this, and just call it the estimator confusion matrix. Those are basically the same thing, huh? Yeah, there's no difference between those two. So let's look at what the decision tree was trying to do. So I want to go from sklearn.tree. This will help us understand like what the decisions were that it was making in terms of the model overall, so we can get an idea of what it was using to make that prediction. So the export text, and then we want to also display the tree. So I'll start here. The decision tree rules. And then we want to go to export text. We want to model. We call it classifier, right? Yes. Okay. And then we want feature names. Preprocessor, right? Yeah, preprocessor. Get feature names. Maybe it's DT. DT model and steps. So what is the issue here? Fallen transformer object has no attribute. Get feature names out. Oh. I think it's just because I made it plural and I think it's singular. Get feature names out. If I try and run this by itself, I get a large array, sure. The value of an array with more than one element is ambiguous. This is the last. Mm-hmm. So this is still returning a list. What does export text require? Let me come back to that one. I'll try and do the tree. Last names. This should be here. What was it? Classes. Use an underscore. If I do that, plot a decision tree. See if we can zoom in on that. Well, that is awful. Let's make this bigger. This boxes still seem tiny by comparison. Let's go here. No, even on the image that it outputs, it's too tiny. That's not particularly helpful. If I change that. Nope, that didn't change anything. Okay. See if making it wider will be more useful. All right, if we really zoom in, we can kind of make it out, but not enough that it matters. So looking here, we want to be able to extract the rules. I take this out. So it just tells me the feature. Save this. Is it really pre-processing? Yeah, pre-process sort. Let's try pre-processing. Let's do that. Let's try pre-processing. Okay, so I need to figure out why this is happening here. When we did, just do all, I'm pretty sure. Yeah, so it must contain 564 elements. If I go here and I get right now, just tell it to give me this back. I want to make sure that this matches 564, which it does. So it gets this out, but it's giving me a list. So it's getting an array, but it's expecting a list. And could I do so this should just be right, or is it to list? In terms of the output here. Yeah, so I think that's the issue, and hopefully that will clear it up. All right, there we go. So then just need to copy this down here as well. I feel like that's missing. Delete this. So now there's more useful information in here, but it's not, I still don't think we can zoom in and see. Yeah, it's not particularly telling us. we can't see what's in there for it to actually be useful. Even when I save the output, the numbers are blurry even on that output. So that part's not very useful. I guess if we go back and we look at the rules that we're seeing here. So if it is the signal back formation, and then it makes a split. Looks like there's a player ID here. It makes another split. So one particular player seems like they are likely to favor a route. So it may make sense that the I'm surprised that the team abbreviation is not a better split for that. It's more of the formation here. Did we include the team abbreviation for the model? We did. So that wasn't the issue, right? Even here. So we have the team, who the player is, the formation. I want to do an experiment real quick. I'm going to try and separate this. I'm just going to look at a single team and see if we can use that as an explainer for what's happening here. So I want to take a single team and then split them out. So I want receiver data enhanced. I want there to be a filter of same thing. We're just going to do Tampa Bay just because we had seen that a number of times already. Great. And we're going to call this TV data. Now what I want to do, I'm going to take a version of this and we're going to make it run purely off of TV data. So do that, and then we're going to split it here, run here. So we get slightly better outcome when we filter for specific teams. Right, and then let's go here. What is it going to say? So we get a little bit better of scattering here across what it's trying to predict as far as the routes go, instead of heavily going into this go route. Right, this is what it looked like before. You can see occasionally it would predict other routes, but for the most part, it was always predicting go. So then what do we see here? The team still ran a fair amount of go routes, but not as many. Then we come back here. And so basically, yeah, now it's heavily dependent on who are the receivers on the field, and then what is their actual alignments. And I'm curious if we would get a much better graphic here, or what the heck's going on. So let's take a look and see. The boxes here are just far too small, I think, to even see at this rate. So we see player. So if it was this player, they are likely to run a go route. Just follow it over to the other side. So if it's that player and the formation is empty, then they're running a flat. And then it's most likely going to be a screen. Right? Otherwise, it's going to come down here. Native yards to go should not be possible. Well, it's the standardized version of yards to go. So it's no longer saying negative 1.2 yards, which is where my mind jumped to. Saying like less than one, negative 1 standard deviation away from the average. So you're saying it's about less than 2 yards to go. It would be a flat. And there were 7 samples of that. It was always a flat there. If it was greater than that and it was a single back formation, well, right, because it's not empty formation. It's single back formation here or not single back. was it first down? Well, then they ran it out. It gets a little bit harder to follow the more levels you go in here. So we're saying that there is only, we're only letting it have, what was that, 6 levels? 6 levels in terms of its prediction. Now, if I let it go, let's say 10 levels down, it doesn't take too long to rerun this. We're going to resplit the data. Our accuracy actually decreases. If I say, give me, I don't know, 4 instead of 6, get 30% accuracy. So it's like the more decisions you allow it to have, you're actually decreasing the accuracy. And then look here. This is where you can see now it's more likely to predict go as their route. That was their most popular route. And so that while that does increase the predictive power for it overall, you're not getting a better or particularly better output here. You're talking here again at that 30% range. So for example, if I said you can only make use 2 things to make your choices here, that's what it would be by the max step of 2. And so it's going to heavily favor go routes again, and then try and make a couple splits for the easier ones to tell. So these are like the more straightforward cases where it was like there's some very clear groups here. So like the flat route, again, very likely, or you can see here it tried to make it, but then look, then half the time it was actually an angle route versus the flat. And so there's just not enough information here. And then, like I said, so we did 2, 4, 6 was the one we had done before. Let's do 8. So you should see more variance in terms of the overall matrix in terms of what it's trying to predict. And we start to see here our accuracy was decreasing before. We've started to go back up a bit. Now, if I said, let's get a little bit crazy, say there's 20. We know there's not 20 overall factors here, but once you include the fact that, right, there are many different combinations of receivers you can get on a play, that's why this can kind of get very large very quickly. So again, we'll resplit the data. You can see here we had a decrease. And I'm going to guess when we look here, it's still going to probably heavily predict go. Oh, wow. So stop predicting go routes more heavily, but still not great in terms of what it actually would be. So you can see here, we actually will probably want to increase this a bit more and work to find what that next is. So let's see. At this point, we're just kind of playing to figure it out because it's such a quick return. We're seeing our accuracy 22% again. Go here. So I'm wondering if scaling the numbers actually creates an issue. So let's change this. And this is only for the model here. Instead of scaling it, let's just say remainder is pass through. I believe that's the right way to do it. Double check that real quick. I have to do it outside of the transformer. Okay. So do that. Let's change this. And so let's go back a bit here. Let's go, we'd said 6 originally. Let's go back here. You can see changing that to the pass-through, our accuracy actually went up significantly. We got that 28%. You can see here. So let's do this. We are going to put a loop here. So let's do this. Find decision 3D testing. What we want to do here is pass in the depth. Everything's going to come in one level. And we want to return so we're setting this up here for in range 5 to 50. DT results. Is that open? And we want to then call, or we want to do DT results dot append I, and what do we call this? Decision tree testing I. And what we want to do at the end, we want to show DT results. The idea here is we're going to iterate across 5 to 50. Exactly one argument. Okay, so I'll change this to here. Change it just to a dictionary. We're going to pass the results in. They'll be ordered anyway, right? Great. So it won't take too long. Oh, yeah, I'm silly. Passing on the inside is going to screw things up. And we get the same results because I did not change max depth to be equal to depth. So what do we see here? Well, once we pass about 24, we don't see a significant increase. Like we've pretty much hit we've tapered off or plateaued in terms of what we can get. And we can see here kind of those numbers in the middle. 14 is a slight jump up for this given team, the Tampa Bay. Otherwise, we're actually fine. Like using fewer is better here for the given team. So we saw 5 was 29%. When we did 4, we saw it was in that same range. So I was wondering if we were going to hit like a wave somewhere along the middle in terms of the accuracy, where we have this, like we're doing well, we're going to dip, and then we're going to kind of jump up and go back down again. But that wasn't the case here. So what we saw is that a fair amount of them got around this 25% range, and then we started to dip until we plateaued at that 22.7% range. So we spent a fair amount of time here, but I think this was good to showcase in terms of the decision tree model, because it's very easy to do visualization on it to know exactly the matrix that we were going to get here. We can also do the same metrics if we wanted to for the logistic tree, and I imagine we would see very similar outcomes here. I think this would be based on like the 50th one that we did. So you'll see, for the most part, predicting one or two labels worked very well for it compared to others where it's just there's so much information for a given situation for it to predict. And again, decision tree works very well when a lot of things are binary, but it seems to struggle beyond that. So saying when we looked here at the rules for it, it was more important knowing who the player was on the given play in terms of what routes they have than other information. And then other factors started to come in, like the receiver alignment, how far to go from the end zone and stuff like that. So there's definitely more to be done here. We're kind of at time for today in terms of what we can get to. So we'll come back next time. I think what we saw here, it may be worthwhile to come back and pick up the thread from last time we mentioned about knowing who the other offensive players are on a given play. I think we'll cover that at the beginning next time, come back and see if that makes a difference in terms of the combinations of players who are there on a given play to get better information out of the model. You can see here, like the score differential started to be a factor. So, is the game close or is it out of hand? Do they start taking more shots downfield? Things like that start to become a factor. And like I said, the players and the alignments seem to be the biggest part here. So I want to see if we can get more information, not just who's the player on that play, but also what are the other players that are on the field with them. It seems like that's fairly important. Some of the situational information here, like I don't see anything. We did see, I guess, one where the case of what was the formation? Or sorry, the distance. There was one that was like a first down, was that they were likely to run a certain route. And then looking here, we're starting to see like the defensive team actually creep in to being part of the prediction. So curious if we can get better output here by adding in the players. And I think that's where we're going to start for next time. So for those of you who came, thank you for watching today. And then if you have any questions, please feel free to leave it on like the YouTube video that comes out afterwards. If you're doing something similar yourself, I'd be happy to help you out when you're running into issues. And next time we'll pick up by putting in the receiver information on the play. So thank you for coming, and I'll see you all be doing this again probably on Friday. So thank you.